Okay, hello. Today we'll be learning about precipitation reactions and other types of reactions in this chapter semester review. So first of all, let us remind ourselves of what an strong electrolyte is and a weak electrolyte. So basically, a strong electrolyte 100% decomposes in water, which is an aqueous solution. So any forms of salt that decomposes 100% in water is a strong electrolyte. And then, like, for example, if you have water here, right, and then you have salt, which is NaCl. If you put NaCl in water, it completely decomposes into Na sodium plus and chlorine minus. So this is an example of something that's soluble in water. So this is soluble in water, right? Soluble. And then a weak electrolyte is something that won't decompose in water. For example, we have this. These are like naturally these compounds. If they're put in water, they will form. They would not decompose inside water. For example, let's say So like an example of an insoluble object, like for example here we have bromine. One of the exceptions to its solubility rule is Ag. So like for example, if you have AgBr, we know that this is insoluble in water. So it's like it's a weak electrolyte. It's definitely not going to 100% decompose in water. So we call this an insoluble compound. So something that's insoluble in compound just remains. If it's like a solid initially, it remains as a solid and it does not decompose into ions. Wait, so AgBr won't be called a weak electrolyte because a weak electrolyte exists between an ion and exists between an ion and like non-ion, because it goes into equilibrium. But AgBr, we call it a non-electrolyte, so it is definitely not going to decompose in water. Like sugar, for example. Sugar is another very good example. So the gist of precipitation reaction is just is double replacement. Wait, hold on. Okay, so basically the gist of a precipitation reaction is just double replacement. So let's say I have this reaction right here. It's the reactant. We have HBr in aqueous and CaOH, right? As our reactants. So basically, to figure out the precipitant, you will do double replacement. So you would replace the Ca here with the hydrogen and the hydrogen with the Ca here. And then once doing this, after replacing the two compounds, right, the two elements, you of course balance it, and then you get a full reaction. So in the end you'll get. So after doing the double replacement and then balancing out the equation, you get this. And then after doing this, you basically write everything in its ionic form except for the insoluble thing, which is in this case H2O. So 2H2O is basically the insoluble product. So you write everything in its ionic form, doing this like 2H plus 2Br minus, and then you'll find. So after writing everything in its ionic form except for the insoluble product, you cancel everything on both sides of the equation. So the Br, the 2Br cancels with this 2Br, and then the Ca plus 2 cancels with the Ca plus 2. And I didn't mean to cancel the hydrogen, but in the end you're gonna get 2H plus 2 hydroxide, which is minus charge, will give you 2H2O, and this is the net ionic equation. This would be called the net ionic equation. Okay, so the next type of reaction we have is called an acid-base reaction. And basically, like, there's different types of acid-base reactions, and one of them is called a neutralization reaction. So basically, when you have a neutralization reaction, you have an acid, right, and is titrated with a base, and then to form salt and water. So let's write this down and give an example. So basically, a neutralization reaction has an acid and a base, and then it forms a salt and water. Like, for example, you have hydrochloric acid, which is very acidic, plus sodium hydroxide, which is basic, forms NaCl and H2O. Another form of a acid-base reaction is a gas formation reaction. So basically, a gas formation reaction, you could have, it takes on two different forms. So basically, you could have a metal carbonate or metal bicarbonate, doesn't matter. A metal carbonate plus a strong acid forms a carbon dioxide gas and water and salt. And then a second form of the same gas formation reaction is a metal sulfide and plus a strong acid forms dihydrogen sulfide gas and salt. So let's just write that down, right? So this is it. Like, for example, if you have a metal carbonate or metal bicarbonate, works the same, plus a strong acid forms a carbon dioxide, water, and salt. So, for example, an example is magnesium carbonate plus hydrochloric acid, right? Because magnesium is a metal, and carbonate, of course. Magnesium carbonate plus hydrochloric acid forms carbon dioxide, water, and MgCl, magnesium chloride. And then another form of the same gas formation form is if you have a metal sulfide plus a strong acid, the strong acid is always there, plus a strong acid forms dihydrogen sulfide, which is just H2S, right, plus a salt. Okay, so this is it for acid-base reactions. Okay, now let's move on with how to balance and also write out a redox reaction. So basically, from before, we know what a formal charge is. Formal charge is basically used for covalent bonds, and just like you have covalent formal charge, you also have ionic charge, which is essentially used for a redox reaction. So basically, for example, H2O, right? Let's write the Lewis structure of H2O, which will look like this: hydrogen here, an oxygen atom connected with two hydrogens. So in this case, we know H2O, which is just water, has if you write the Lewis structure, it would look like this. And you know that oxygen shares an atom with hydrogen, right? So there's atoms at the end of this Lewis structure, let's say. And basically, if you could see the amount of electrons the oxygen is sharing, you could compare that with the valence electrons, the amount of valence electrons in its outermost shell. And then so basically, in this Lewis structure, the oxygen atom shares 6 electrons. 1, 2, 3, 4, 5, 6. So I'll denote that by separating it. Oxygen atom shares 6 electrons, right? Shares 6 electrons, and naturally, an oxygen atom has 6 valence electrons in its outermost shell. So 6 electrons in its outermost shell minus the amount of electrons it actually shares, which is 6 in this case. It gives you a formal charge of 0 for oxygen. So the formal charge of oxygen would be 0 here. Just like hydrogen, the amount of electrons in its outermost shell is 1, and the amount of electrons it shares is also 1. So formal charge here would be 0, and the formal charge here would be 0. This is how you figure out the formal charge of a 100% covalent bond, if you assume it's 100% covalent bond. So basically, if you assume that this oxygen, let's say, was a ionic bond, right? If you assume it was an ionic bond, you would say that since oxygen is the most electronegative here in this molecule, it will want to hog the electrons. So if it's hogging all the electrons, since it's more electronegative than hydrogen, it's gonna hog all of the electrons here. It's gonna hog all of the electrons. So in this case, so this is what you do when you have an ionic. If you assume it's an ionic compound, so since oxygen is the most electronegative, it's gonna hog all of the electrons. So let's say, since we know that oxygen for sure has 6 valence electrons in its outermost shell, you would subtract that by the amount of electrons it's actually taking away from hydrogen. Since if you assume it's an ionic compound, electrons are transferred instead of being shared. So 6 minus 8 would give you -2. So oxygen, you would say, would have a oxidation number of -2, and hydrogen would have an oxidation number of +1, since you would just do 1 minus 0, since all of its electrons are transferred to the oxygen. So it would have a oxidation state of +1 here, an oxidation state of +1 here as well. So if you add all of this together, you say H2O is neutral. If you add -2 plus obviously 2 would give you 0. So this is how you would work. So for redox reactions, we really want to stress this form, not the formal charge form, but the ionic form of figuring out the charge of a molecule.